Hi, I'm Dane Quinn from the University of Akron, and let's do another example dealing with rigid body dynamics. So here's the problem. We have a bar of mass m and length L that is pinned at O, and the bar is uniform so that the mass center of the bar is located here at G, and it's released from rest at an angle theta. Here, release from rest implies that the initial angular velocity of the bar is 0, and I'd like to find the resulting angular acceleration at this instant, namely when it's released, as well as the reaction force at the pin at O at the same instant. So we certainly have gravity that acts on this system, and essentially the bar is going to swing back and forth as it undergoes its motion. So looking at the bar itself, let's identify the forces that act on this bar. Well, there are two of them, right? One is the weight due to gravity. So we'll say W. So that's certainly one force that acts on the bar, and the second is due to the reaction at the pin. And so we'll call that force R. R for reaction. So again, we have this reaction force, and the reaction at O is unknown, right? I have no real information about what this force is. I don't know its magnitude, I don't know the direction, I don't know anything about components. It's just some force that acts at the pin. So now, let's move on and look at the coordinates and directions that we need to define to describe the configuration of the bar, its motion, and hopefully any forces that are acting on this. Well, theta works as a coordinate, right? And it was given in the problem statement. So if I know the angle theta, I can tell you everything about the configuration. In particular, I can tell you where the bar is. Now in terms of directions, let's define I and j like so. So, kind of standard, horizontal and vertical. And then let's define E1 as perpendicular to the bar and E2 as a direction along the bar. So with this, the angle theta lies between I and the E1 direction, and also between J and E2. So again, theta describes the orientation of E1 and E2 relative to I and J. So with the coordinate theta in the directions I and J and E1 and E2 defined like so, I can relate these two frames of reference. And so in particular, I can be written as cosine of theta in the E1 direction minus sine theta in the E2 direction, while J can be written as sine of theta in the E1 direction and cosine of theta in the E2 direction. Likewise, I can go and write E1 in terms of I and J. So E1 is cosine of theta I plus sine of theta in the J direction, and E2 is minus sine of theta in the I direction plus cosine of theta in the J direction. So again, these are two frames of reference that are going to be useful. The weight, the gravitational load, is in the J direction, right? So it makes sense to define that. The directions that are natural to describe the configuration of the bar are E1 and E2. Right? So those again are perpendicular and along the bar, so we want to define those. Then with the angle theta, it's easy enough to relate those two frames of reference as follows. So now let's turn to the kinematics. Well, the angular acceleration of the bar is given in terms of theta double dot. Specifically, alpha of the bar is theta double dot in the k direction. Right, so the direction that is perpendicular to the plane of the paper or the computer screen or whatever it is you're watching this on. And now I need to find the acceleration of the mass center. because when I go to apply linear momentum balance, I need that, right? I need the acceleration of g. Now, I'm not measuring the acceleration, or I'm not measuring the position or the displacement of g directly. Instead, I'm measuring theta. So I need to be able to relate the coordinate theta to the acceleration of g. And I can do that using planar kinematics because O is fixed in the ground. So we can write the acceleration of g as the acceleration of O, because again we know something about O, and it's fixed in the bar, plus the angular acceleration of the bar cross the position of g with respect to O, plus the angular velocity omega cross r of g with respect to O. So now with this, the angular acceleration is given here. The angular velocity in terms of theta is simply theta dot in the k direction. The position of g with respect to O is minus L over 2 in the E2 direction. So now taking these and inserting them into this equation, we have the acceleration of g is 0 because that's the acceleration of the pin, plus theta double dot in the k direction cross minus L over 2 E2 plus, and then omega cross r. So that's theta dot k, another theta dot k, and then minus L over 2 E2. So when I work out all these cross products, k cross E2 is minus E1, but I have another minus sign there, so I end up with L theta double dot over 2 in the E1 direction. And then working out this cross product, I get plus L theta dot squared over 2 in the E2 direction. So again, in terms of the angle theta and how it changes, this is the acceleration of the mass center. Of course, the bar is released from rest, so at t equals 0, and that's the time that we're interested in, the angular velocity of the bar is equal to 0. So theta dot here at time 0 is equal to 0. So now we turn to a free body diagram, and we need to go through and describe the forces that act on this system. Well, the weight is relatively straightforward. That's simply minus mg in the j direction. So the reaction force, remember we said we knew nothing about it. I don't have any information about it. It's not given in terms of any specific components or directions or anything like that. So really it has two unknowns, and I'm going to represent those as the magnitudes or the components in the E1 and E2 directions. So here we'll break this reaction force up into R1 E1 and R2 E2. Right, so again, the reaction force, because I have no information about it, I am just going to write that as R1 E1 plus R2 E2. Now I could just as well express this in terms of I and j and write something like Rx in the I direction and Ry in the j direction. But what we'll find is later on, the algebra is a little simpler if we go ahead and use the directions that are intrinsic to the bar, which namely are E1 and E2. So again, I could use I and j. It's just that the algebra would be a little more complicated later on in the solution. But if you do use I and j, everything still works out fine. You have a number of equations and unknowns, and you can solve and get the same answer that we will get eventually. So now let's turn to the equations of motion. Well, we have linear and angular momentum balance. So linear momentum balance for this system, namely sum of the forces is mass times acceleration, ends up looking like the following. Right, so again, sum of the forces. Well, acting on the bar, the forces are R1, E1, R2, E2, that's the reaction force, minus mg in the j direction. And this equals the mass times acceleration. So that's ml theta double dot over 2 in the E1 direction plus ml theta dot squared over 2 in the E2 direction. Again, this right-hand side is simply the mass times the acceleration of g. So now I can take components. But the question is, what direction should I take components in? I really have two choices. I have E1 and E2, or I have I and j. Now if I look at this equation, almost all the terms are in E1, E2. So it just based on that, it kind of makes sense to change j into E1, E2. Again, we know how to do that. Right? We did it on slide 1 over here. But I think more important than that, if I look at the unknowns in this problem, well, theta dot at time 0 is 0, so that vanishes. But I don't know theta double dot, I don't know R1, and I don't know R2. However, I do know m and g. So again, the unknowns here are nicely split in terms of E1 and E2. So if I take components in the directions that sort of naturally split the unknown variables, again, the algebra is going to be simpler. Right? So let's go back and recall that j, again, from our description of the coordinates and directions, was sine theta E1 plus cosine theta E2. I'll just write that down just to remind ourselves. And so now, in the E1 direction, we get R1 here, and now we have a term in the E1 direction minus mg sine of theta equals ml theta double dot over 2. And in the E2 direction, we have R2 minus mg cosine equals ml theta dot squared over 2. And eventually I can make use of the fact that at time 0, theta dot vanishes. But for now, I'll just kind of leave it in, and then we'll introduce that later. So the next equation is angular momentum balance. Well, if you recall, we can easily take angular momentum balance about 3 points. Right? One is about the mass center, which always works. The second is about a point that is pinned in the object and pinned in the ground. And we have such a point in this problem, namely point O. The third case was the case where we're dealing with rolling without slip on the ground, and that doesn't apply here. But let's go ahead and take angular momentum balance about point O. Because when I do that, the moment from the reaction force vanishes because it acts at O. So the moment about O from the reaction force vanishes. So again, that force acts at O, so it produces no moment about O. Instead, the only moment is due to gravity. And I think I'll go ahead and calculate this sort of according to the definition of moments due to forces. So that's going to be R cross F, in particular R of G with respect to O cross the weight. So the position of G with respect to O, we've already said, was minus L over 2 in the E2 direction. The weight is minus mg in the j direction, right? But of course j was sine of theta E1 plus cosine of theta E2. And so when I evaluate this cross product, E2 cross E2 vanishes. E2 cross E1 is minus k and then actually 2 more minuses, so ultimately I get minus mgl sine of theta divided by 2 in the k direction. So, angular momentum balance, sum of the moments, about point O, is equal to, well, this is the only moment, minus mgl over 2 sine of theta in the k direction, is the moment of inertia. Well, for a bar, the moment of inertia about the end is ml squared over 3 times the angular acceleration, which is theta double dot, in the k direction. So now we have equations for linear momentum balance, and these are the components, and angular momentum balance here. So notice that angular momentum balance only has components in the k direction. The only moment that acts on the bar is in the k direction, and I alpha is also in the k direction. So, taking components in the k direction, yields the following. Minus mgl over 2 times sine of theta equals ml squared over 3 times theta double dot. So, we can solve this for theta double dot. And that yields theta double dot is minus 3g over 2l times sine of theta. So we've used angular momentum balance to directly solve for theta double dot. And finally, returning to the definition of the angular acceleration. Remember, the angular acceleration of the bar was theta double dot in the k direction. So we find the angular acceleration is minus 3g over 2l times sine of theta in the k direction. So this total expression here represents the angular acceleration of the bar. Now, obviously, it is essentially theta double dot, but the fact that it's in the k direction is important. Angular acceleration is a vector. Vectors have magnitude and direction. So here, the magnitude is theta double dot, while the angular acceleration is in the k direction. So really, we need both pieces in order to properly describe the angular acceleration. Now, looking at the reaction force, we can go back and solve for R1 and R2. And when I look back, let's go back a slide, we see that R1 depends on theta double dot, while R2 depends on theta dot. So, in particular, I can solve for both R1 and R2 as mg sine of theta plus ml theta double dot over 2, while R2 is equal to mg cosine of theta plus ml theta dot squared divided by 2. Now, theta double dot was one of our original unknowns, but we've already solved for that. That was our previous step. So I can actually take this expression for theta double dot and introduce it here into the reaction force for R1. Notice that R2 does not depend on theta double dot, but it does depend on theta dot. However, theta dot was given as one of the initial conditions. In particular, theta dot at time 0 was equal to 0. So, these two may be determined as R1 mg sine of theta, and then here this reduces to minus 3 mg. Notice the L in the denominator cancels out with this L. Minus 3 mg over 4 times sine of theta. And so R1 is simply mg over 4 times sine of theta. R2 reduces to only mg cosine of theta. Again, that's because at the initial time, theta dot vanished, so theta dot's equal to 0. And that simplifies R2 considerably. So again, the reaction force is a vector. So these are the components of the reaction force in the E1 and E2 direction. So the final reaction force can be written as R equals R1 in the E1 direction plus R2 in the E2 direction, or finally plugging in for the components, mg over 4 sine of theta in the E1 direction plus mg cosine of theta in the E2 direction. And that's our expression for the reaction force. So we're able to solve for both the angular acceleration of the bar and the unknown reaction force between the ground and the bar located at the pin joint. So again, the component of the reaction force in the E2 direction depends on theta dot squared, but at this instant that term vanishes. However, as the bar begins to swing, theta 2 dot squared will always be positive, so that will actually increase the reaction force. The reaction force is larger when the bar is moving versus when it's not moving or at rest. So that's it for this example. And here we've looked at an object that has a point fixed in the ground. So the distinguishing feature of this problem is that we were able to take angular momentum balance about that point, which eliminated the reaction force sort of directly from angular momentum balance. And that enabled us to solve for the angular acceleration in a pretty straightforward way. So that's it for this example. Thank you very much, and I will see you later.